practice problems, you guys can finish your problem set in class, my goal. Okay? Now, make sure that everything is done by tomorrow. That's including missing work or things that if you've been out for AP exams, like for example, I think I've got a couple of you guys let me see 1 through 8 to 4 from molarity, molality, percent solutions. So when everything is done, we are making ice cream tomorrow, okay? So that includes your rainbow lab. If you haven't put your rainbow lab, you know, the lab we did yesterday? Some of you guys weren't here yesterday. You guys are like, your faces are like, what is she talking about? So the rainbow lab will go in the box. If you were not here yesterday, we can get you data. The data is information that you'll use to do some calculations, and then there are some questions that regard information about how solutes and solvents interact, and then what differs because of that, okay? All right, so we'll jump on that kind of towards the end. Let's jump into some notes. Information here, you should be able to tell me quickly how each of these dissolve or react or interact with water. What's the name of this first guy? Sodium bromide. In your head, you're going ionic or covalent? Ionic. Syrian, how do ionics dissolve in water? Like what happens?
Well, usually you put it in there, then you have to add, you have to stir or add like something for it.
So if you zoomed in really, really, really far and you looked and you saw this and this, what would they have become?
They would have attached to the particle positive and negative sides of the water.
Okay, so are you saying that they would have broken apart?
Mm-hmm.
What's the word we use for breaking ions apart? Ionize, right? These would have ionized. So note to self, ionic compounds ionize in water, and they make sodium ion and bromine ion. And you're right, with that, with respect to water and its polarity, you're going to have some water interacting. And how do I draw water?
It's a spin.
Spin structure. What's on the top? What's the what? The oxygen. Okay, so the oxygen here, H, lone pairs, because that's how you get your octet there. That's kind of oriented towards the sodium, and what's going to orient itself towards the bromine? The hydrogens, right. So this is background information. I think it's valuable to see the drawings because it gives you information on how they interact. So basically these ionize, right? What about this one? We have calcium what? Calcium chloride. Okay, so how does, so in your head you're thinking ionic or covalent? Ionic again. So it's going to do what?
Attention students taking the AP World History exam, please report to the auxiliary gym for check-in at this time. Also, students taking AP Statistics, you will eat an A lunch before checking in. Again, students taking AP World History, report to the auxiliary gym hall for check-in, or the comments for check-in. Students taking the AP auxiliary gym, students taking statistics this afternoon. You will have a lunch before check-in.
Okay, so this is called a dissociation equation. This was number 6 or 7 on your problem set. When I asked to write a dissociation equation, it actually means like how does it ionize or how does it dissociate in water. So sodium chloride makes how many ions? I mean, this was bromide. Bromide, okay. It makes 2 ions. Then we're going to call that an I up 2. If you are not writing these dissociation equations and writing down some information, you need to. Okay? I shouldn't have to tell you guys to take down information. All right, so there's this factor, it's called the Van 't Hoff factor, and so the scientists in it, you know, they like to kind of name some things after themselves, of course. So Mr. Van 't Hoff said that different types of compounds ionize or interact with water differently, and so with respect to ionics, they ionize, but they can ionize into different number of particles. I is the number of particles, not really number of ions, but with ionic, that does make sense. So you tell me, if this is calcium chloride, CaCl2, how will it dissociate? We're just actually assuming that this is solid and that when they go into water, they're aqueous. We're just not writing out water because I don't want you to think of it as a reaction. It's just a process of dissolving. So how will this ionize? Right, what particles here?
Calcium and chlorine.
Calcium like this?
No.
Ca what?
Ca positive.
Positive what?
What?
No.
What? I mean positive 2.
Right, because calcium has this 2 came from calcium, right? So it's a 2 plus charge. And then also it makes what? Everybody.
Chlorine.
Chlorine, how do I write that? 1 minus, right? Okay, so I've got calcium and I've got chlorine. But then if we're thinking about the balancing, you want to add to that? We're talking about like balancing how many ions or how many elements we have over here on the reactant side as we make products. What do you see that's different?
Well, there's 1 calcium and 2 chlorine.
And there's 2 chlorines, right? So then we have a difference here. This was 1 and 1 because there was a 1 and 1 subscript. And over here we have a 1 and 2 subscript. So that's 1 and making 2 chlorine ions. What's the I factor? 3, right? Because we have 3 ions made. So that's going to cause a difference when we're actually talking about the colligative properties, which are solutions and their properties that they attain. So when this ionizes, it makes calcium and chlorine. So these 3 ions actually act a little differently than the 2 ions do. Water still interacts in a similar fashion. Now, last one over here is ethanol. Ethanol is C2H5OH. Thinking in your head, ionic or covalent? Can I get a vote? Ionic, covalent. Most of us are covalent. So what are you looking for here? How do you know it's covalent? All nonmetals. Do you see a metal there, period? No. Okay. Do you see any polyatomic ions? No, don't. That is not hydroxide. Sorry, that's an alcohol group. That's an alcohol group. And that's actually what this little OH up here is, that group, that red and yellow or white thing is. So it's not ionic, so it's covalent. It's kind of like sugar, so sucrose. Will it ionize in water? Yay or nay? Loud and proud. No. Okay, so in this case, it's going to stay as C2H5OH, and it's not going to dissociate. It's not going to ionize. It will just get surrounded by water. Water just kind of like hangs out, and it's called a hydrate. It surrounds it like this just to kind of hold it into solution, so it would look like it wasn't a solid. So in this case, what's my I factor? How many particles do I have according to this dissociation? 1. I is 1. Because it did not dissociate, it still is maintaining its singleton self or singular self. Okay, so who definitely is going to make more than I of 1? Anything what? Ionic. And then covalent things, we're just going to say they don't dissolve, they don't ionize, they don't dissociate. There's many ways to say that, but they will always have a Van 't Hoff factor of 1. So what I've been saying for Van 't Hoff factor is this. Van 't Hoff factor. And that is just the number of particles made from those dissociation processes. Van 't Hoff. And that's called the I factor. So far, so good, guys?
Yes.
So we're going to use that kind of logic in the background as we talk about colligative properties. Some of those colligative properties are things you guys learned about in your readings. What were some of the things you guys learned about in your readings? What were your main topics? Avery, what was your reading from yesterday?
Water.
Oh, and Flint. Okay, so his was more about equilibrium. So actually, hold on. What, Siri, what was your reading? Close reading. Okay, I'll come back to you. Shelby, what was yours? Okay, and so that's actually about dissolving sugars versus maybe some ionic compounds. Kaylin, what was yours? Flint. Who had salt? Okay, so what was yours about?
It was about how salt is used to dissolve ice off roads.
So it's kind of like allowing ice to not even form in the first place, or maybe forcing it to melt.
Yeah, it makes the street warmer.
Okay, and so that's actually called freezing point depression. Who read the ice cream one? Okay, so I've got a couple people reading ice cream. That's called freezing point depression as well. We actually depress the freezing point of milk, so it freezes at the temperature at which we're holding it to. So we're going to make ice cream tomorrow, so that's why we're talking about freezing point depression quite a bit today. All right, so one more property before I get into the actual colligative properties. These are 2 situations that you guys who did the live yesterday dealt with. What kind of solutions were we making whenever we were just making our solutions and building our little rainbow column? Electrolytic solutions or non-electrolytic solutions? Why do you say electrolytic? Because they were all conductive, right? So electrolytic comes from the fact that we have electrolytes in solution. And so you're saying electrolytes make the solution what? Conductive. So they allow for electricity to be conducted through the solution, or we can just call it a conductive solution. And those kind of, the solutes we were making from our solution standpoint yesterday, who was in the lab yesterday? I'm trying to remember who was all here. We had a small class. Okay. What did we put in our solution? What salts everything? We put sodium chloride. So basically, conductive solutions are anything that are solutions with ionic compounds as their solutes. And we're going to learn later that some acids and some bases can do that as well. But starting right now, it's just salts that ionize. They make sodium ion and chlorine ion, for example. These ions are what make it conductive. So when you throw an electrical current through it, which is coming from this battery, and you have to complete the circuit, these little ions in the solution allow for the circuit to be completed, so the battery sends its electricity through. It kind of gets shuffled through the ions. It moves up to the other side. It lights up the light bulb, and it continues. Who's learned about circuits like in 7th grade? You got to complete the circuit for it to work, right? So what do you see? What can you imagine down here that's happening? It's what? Not complete. Okay, so it's not conductive. So we have to send the electrical current through. It goes through this little wire here, and then what's in the solution? Maybe what's not in the solution. So right, so not ions, right? So there's no ions here. So what would be some good examples of non-electrolytes, things that don't ionize? Covalent things, right? We really got two options here, ionic or covalent. Another word for covalent compounds is molecular. That's just another term for that. So they are non-conductive because they don't ionize in solution. Pretty simple concept so far? Yeah. We will get into the extra details with this, with acids and bases, which is next week. Give me a thumbs up when I can move on. All right, cool. So, we're not going to do that right now. All right, so the whole big idea of colligative properties today are based on that very, very beginning slide where you were looking at ions being produced or the ethanol not ionizing. So that's what this reading right here is pertaining to. They're properties of solutions. So properties that we've talked about before are boiling point, melting point, freezing point, color. They're all those physical properties. But when you start to mix things together, make solutions, you actually can change that. You can modify the boiling point. You can modify the freezing point. You can modify the pressure that the vapors make when they come off the top. So it's really specific to the solution perspective. We have made a solution. After we put solutes and solvents together. So these properties we're modifying, which are these physical properties that we're modifying, freezing point, boiling point, and vapor pressure in particular here, they will change in magnitude based on what we put in the solutions, be it ionic compounds or covalent compounds. So the fact that we're looking at the number of particles, which is the I factor, or the Van 't Hoff factor, is important for us to consider as we look into how much the freezing point gets depressed, or how much the boiling point gets elevated, or how much the vapor pressure gets lowered. So the magnitude of these changes are dependent upon the number of particles there. This is probably the longest slide, and then I have like a math-heavy slide where we can do calculations. So basically, this whole group of properties these three right here, and actually another one that we won't do calculations with unless you go to AP Chemistry. Osmotic pressure is the fourth one. You probably think osmotic kind of sounds like osmosis. It deals with like cellular pressures inside that allow water to flow back and forth between cells. It's pretty advanced. But your cells have saline and stuff and organelles and sugars and proteins. There's a lot of things that can affect the pressure that's inside the cell versus the outside the cell. So osmosis will change based on that. But the whole idea that all these properties can be changed by adding solutes, the whole group of properties is called colligative properties, but specifically we will delineate these right here. All right, I'm going to move forward here in a second. Just going to scroll down a little bit. If you don't remember, these are this green down here, so some reminders. If you forgot what vapor pressure is, because sometimes we do, it actually is the point at which you have vapors coming off the top of a solution. So the vapors that are forming, let's say in the closed container, make it a closed container, the vapors that are coming off the top of the solution, what are they doing with the container wall? They're colliding, right? They're hitting the container wall, they're causing a pressure. So that's one idea to think about it in terms of vapor pressure. But when you're thinking about it in terms of boiling, which you'll start to see 1 and 3 here, they'll start to relate to each other eventually. It is the point when the vapor pressure and the atmospheric pressure are equal, and so the vapors can start pushing past the atmospheric pressure, which would be when something would boil. So the vapor pressure that's coming from the solution and the boiling or atmospheric pressure that's coming from the top would become equal. So it's actually more of the definition of boiling than vapor pressure. Give me a thumbs up when I can move on. Here, very time. Okay, so let's look at some pictures and try to understand what this is actually referring to, and then we'll do the calculations. Calculations really come in one equation, it's just you modify pieces of it. So here's our vapor pressure lowering. So remember, the only one that's up is which property. Boiling point gets elevated, everything else gets depressed or lowered. So vapor pressure lowering is going to be with respect to the solution that's pure versus the one that, this is like pure water, for example, versus so I wouldn't call that a solution, that's just pure solvent, versus like water with sodium chloride or something like that. So we're looking at the difference in vapor pressure that these two have. Pure water is going to have a lot of vapors that are able to come off the top of the solution, which you can kind of see up here. These blue guys are water, and they're starting to vaporize. So the vapor pressure would be high because there's a lot of vapors coming off of it. But what happens here is, let's think back to the pictures, and these pictures that you guys have been drawing and you guys drew on the day I was out are important here because it helps you understand what is the little positive ion doing with the water molecules here. What kind of interaction? Kind of IMF? Yes, they are actually interacting through a pretty strong intermolecular force, which we've been calling ion dipole, but you can still just think of it as a strong intermolecular force. So if these water molecules want to jump out of solution and they want to vaporize, but they're interacting with the ions, are they likely to vaporize? No, they're staying stuck to the ion, and so they're not going to pop out of solution and form vapors. So less vapors, less vapor pressure. It's all very linear. That's very logical. So they're less likely to escape the solution. That's vapor pressure for you in a nutshell. Now, the freezing point information, these are some examples you would want to note and kind of like understand like where they are used in everyday life. We're going to talk more extensively about salts on icy roads to depress the freezing point at which ice would form on those roads. We'll talk extensively about making ice cream. And then who drives? Who's a driver? Okay. I have one student who, she's like a sophomore in college now. He still does not have his license. He takes Lyft everywhere, from Raleigh and back. And I was like, that is lame. You cannot take Lyft for the rest of your life. You've got to get your license. So when you get your license, you have to be very aware of like your car and what does it need? How do you change a tire? How do you check for oil? How do you check for oil's letter? A light comes on. Okay, so we're spoiled. Okay, so we put the dipstick in there and we check to see how much oil is there. Okay, what if your car's temperature starts to overheat? What does that mean? It's not good. That is a, what did you say? Say again? Possibly enough coolant. It could be a number of things, right? But probably coolant is actually radiator fluid. Radiator fluid is the same thing that either stops the car from overheating and stops the car from being too cold or possibly freezing. So it's called antifreeze. So you put antifreeze in your radiator as well. It works for both ways. So we'll talk about how that's a freezing point depressant and a boiling point elevation piece. So I'm going to give you the pieces at first, and then we'll do some calculations. And boiling point elevation, this is something that you probably use often. Who's ever cooked spaghetti or pasta or something like that? Okay, you guys put the water in, and then what do you do? Say what? Okay, so you put the water in, you let it boil, put the pasta in, and then what probably starts to happen sooner than you want? Starts to bubble up and boil over, right? And you're like, oh no, has anybody learned what to do when it starts to boil over? Not take it off. Put what in it? Okay, yes, that's like an old wives' tale. Anybody else? Turn it down. Turn it down. Put salt in it, thank you. Who's ever put salt in it? I didn't hear you. You're chatting. I didn't know what you were talking about. So yes, you put salt in it. So you put salt in it, and so when you actually add salt to your water, it actually lowers the boiling point, or actually it elevates the boiling point, sorry. Elevating the boiling point means it's at some temperature, right? It's boiling, it's boiling, it's boiling. You put salt in it, what's it going to do? What's it going to do next? Not boiling. It's not boiling. Okay, so you're going to have to heat it up more and more and more, and then it'll meet its new boiling point, and then it would start boiling, and then you freak out again and go, what do I do now? But no, our stoves aren't going to usually, hopefully, get that hot. So we will deal with boiling point elevation with most of the time cooking, and it can be actually utilized in other areas as well, but most of the time cooking. So how does this part work? So I'm going to go back to freezing point depression. We learned briefly about how water freezes. So we get 6 water molecules, and what do they do when they solidify? They form a what? What kind of crystal? Which shape? Seeing what you guys remember. A hexagon? Very good, guys. Okay, so I'm going to draw it like this. Starting to become a hexagon. Yeah, okay. 1, 2, 3, 4, 5, 6. Okay. Yeah, it looks like a hexagon. Okay, great. So when they're liquid form, they kind of flow everywhere. They still have some hydrogen bonding going on, but when they freeze, they actually freeze with a gap in the middle, which has what in it? No. Okay, it probably does have air, but I was gonna say nothing. Okay, so maybe it has air. I'm not sure, but it has nothing in there. So what's so special about ice? It floats, right? So the density of ice is different than liquid water. So when all this stuff is happening, it's just the molecules are slowing way down, because as you decrease the temperature, what else are you decreasing? Kinetic energy. Thank you, who said that. So when you're decreasing the temperature, you're decreasing the kinetic energy. They start to slow way down. They're slowing down, they're slowing down. And so then as they start to kind of meet up with some other water molecules, they start to form their hydrogen bonds, which are what these are, all the way around. Those are all hydrogen bonds. And so then they take on this kind of appearance of a crystal, and that's our ice. Well, salt comes in, so salt can be like magnesium sulfate, sodium chloride, magnesium chloride, calcium chloride, a lot of chlorides out there, and those are salts that we can put on the roads. So they come in here, they're like, dun, dun, dun. They start getting in the way, okay? And then when they start getting in the way, what's hindered? The hydrogen bonding process with water. So water can freeze or not freeze at this point? Probably not freeze. So you're going to have to like depress the kinetic energy so much more, because all the salt particles are basically hindering the freezing process. So when the kinetic energy slows down even more, then they are like, okay guys, we have no option. We have to freeze now. I don't care if there's salt in the way or not. We have to freeze. We have to solidify. So what have I done to the freezing point? Depressed it. I've pushed the freezing point from 0 degrees Celsius to -5. Well, in North Carolina, does it get -5 degrees Celsius? No. So we will come to school, no matter if there's ice or not. Now, some roads don't get as much salt, so that's why we actually, sometimes have delays and stuff. So That is what's happening when freezing point depression is occurring. Salt gets in the way, it can't crystallize. It can't crystallize, it has to slow down even more. Hence, slowing down is lower kinetic energy. Low kinetic energy is cold, or lack of heat. Excuse me, misspoke, lack of heat. Okay. So this is the next, and this is kind of the last big slide with information. We're going to look at these equations here in a second. Let me let you read first, and I'll explain. This is so volatile. Volatile, not volatile. You write down the pieces first, and then when I say it again, it'll sink in. I'll write down most of what's on this. So what concentration unit are you starting to see now? Molality, not molarity. Okay, so just kind of keeping that in mind. The little m is intentional, it's molality. So this is where we actually get to utilize it in a calculation standpoint. We utilize it because we're looking at how much I have of the substance, meaning concentration, meaning molality, but not only how much I have of it, but how does it interact with the solvent? Does it ionize or does it not? Because remember, colligative properties depend on the number of particles, not just how much I have, like grams wise or moles wise, but how do they dissociate? Because ionic things can make a significant impact on delta T. These delta T's over here, these are just going to be the changes in temperatures that are occurring, be it boiling point elevation or freezing point depression. It's still a temperature change difference we're looking at. And so we have to include the I factor because it does differ based on the type of compound, like ionic or covalent, that comes in. So whenever I say non-volatile covalent compound, that means that we're going to be using the I factor of 1 because does it ionize? Does it dissociate? No, so just keeping those two terms somewhat similar for now. But non-volatile also means that it doesn't vaporize easily, meaning it's going to stay in that solution, so we're not like losing molecules, so it's going to impact the freezing point or boiling point. Whereas ionic compounds will differ, so the I factor will be greater than 1 as we move along with that information. They are strong electrolytes. So the general equation is delta T is equal to KIM. K is the molal freezing point or boiling point constant. So K is the molal freezing point or boiling point constant. And those are in your book. Do I remember what page? Yeah, right here. Okay. Those are in your book. There's a big chart of them. I have them here for you shortly. But the two that we will use most frequently are for water. Usually water will serve as our solvent. Not every time. You'll start to see that I use benzene and chloroform and some other things, and that's why I can get the textbook number. But for water's freezing point depression, it's 1.86 degrees Celsius per molal, and for boiling point constant, it's 0.52 degrees C per molal. So we'll use that as our K value. That is regarding the solvent. Be very specific there. The I factor is regarding the solute. I have to look and see how many ions it dissolves into or not. So the K is for the solvent, I is for the solute. M, molality, is what? Units wise, whatever what? Moles of what? Solute over kilograms of solvent. So it's kind of both, right? So you got to keep in mind who's a solute and who's a solvent as you work through these problems. Otherwise, we're dealing with Celsius again because temperature changes in terms of like boiling point or freezing point, not gas laws. Remember, gas laws use what for temperature? Kelvin. Good. All right, so let's just practice this one more time so that I understand you know what you're doing here. Can you tell me how many ions magnesium chloride dissolves into?
3.
3, because it makes Mg, 2 plus, and
Cl.
Cl minus, and how many of those? 2, because of the 2 coefficient there, so the I factor is 3, okay? Let's do this one over here. What does the calcium carbonate dissolve into?
4.
Let's think about it. What 2 ions came together to make this?
Oh, yeah.
Magnesium and chlorine. What 2 ions came together to make this? Calcium what?
Carbon.
Calcium charge? 2 plus, and
Yeah.
what's carbonate?
1 minus.
CO3, 2 minus, okay? Most of you guys, if you hadn't really thought about it, you would have broken into Ca, C, and then 3 O's, which is not the case. This is calcium carbonate with 2 ions in it, so it makes calcium and carbonate, so the I factor is 2. There's 1 ion here, and there's 1 ion here. Basically, you just add up the coefficients, and you have the I factor. So the I is 2. Let's look at this one, aluminum oxide. Al2O3 breaks into what? So aluminum with a charge of what?
3.
3 plus, so that's the Al with a 3 crossed down here, and who?
And then 2
So oxygen with a
2 minus.
2 minus charge. This is not diatomic oxygen. That's like in a standard state of non-solutions. These solutions always make ions. How many aluminums do I have according to the reactants? 2. And how many oxygens do I have? 3. So it's my I factor. 5. That makes a significant impact on the freezing point or boiling point, whereas these other ones, the I of 3 or an I of 2, not so significant. That's a big dip there. But aluminum's pretty toxic to, like, aluminum ion would not be good to have in, like, species on the planet there. Okay, well, this is a great slide. All right, so I'm just going to skip that for a moment. We just did that. And I'm going to go to the calculation standpoint. Now, these I don't have on your paper, but I do have some that we'll work through really quickly on ours. So when we're doing these problems, write down your givens like normal, and then we'll go through and figure out how to solve them. So, Ashton, tell me some of the givens that you're seeing here. Okay, so 2.65 moles of sugar. And sugar, thinking out loud to yourself as well, ionic or covalent?
Covalent.
How do you know?
There's no.
Right, this is definitely covalent. There's no metals. Oops, that says code. Okay, so that's I'm just gonna put sucrose here. Okay, Zach, what's another given you see?
It decreases the freezing point at 2.5.
So the sugar is added to what? To 2.5 kilograms of water. Okay, so the sucrose is going to be something. The 2.5 kilograms of water will be important. The fact that it's covalent is going to give us some information. And it says its freezing point is going to depress. How much will it decrease the freezing point is our question. You see that's kind of like blended in there? So the delta T for the freezing point is what our question is. Yeah, I don't have a set meeting right now. I don't know why that just went off. Okay, so back here. So you're seeing all this information. You already know, and I'm going to read the rest of this in a second, you already know the general equation for any freezing point or boiling point elevation question is what? Delta T equals Chem. Okay, so KIM, that's our malal freezing point constant, the I factor, and then the molality. Do I have any of those? No, not yet. I got to derive them myself. Oh, but I do have the K factor. You guys just write this down. What's the KFP? K freezing point depression.
1.86.
1.86, and we're dealing with that one because what's our solvent here? Water, and water is our solvent, so that's why we can use that. So we have the K. What's the I factor of the solute? Why 1? Because it's covalent. I factor is 1. Okay, so I've got the K, I've got the I need the M. How do I get the M? Using all this information. over, got it? Okay, so take my 2.65 moles of sucrose, which is my solute, divide it by the 2.5 kilograms of water, and I get molality. You guys are going to have to tell me what that is here. Wow. Yeah, okay. So I've got everything I need. I can plug it in. What's my K? 1.86 degrees C per molal. What's my I? 1. What's my molality? Squeezing it in here, 1.06 molal. Okay, what cancels? Molality. And what unit remains? And doesn't that make sense? We're talking about temperature, right? It should be a degree, or it should be some sort of temperature unit. Calculate that, guys. You should have calculators around. Come grab this little. Or you got some work behind you. What's that temperature change? One more time, Will.
1.9716.
Okay, so what does that even mean? I have a temperature change. What do we calculate? That's how much the freezing point lowered by. So that means that up here we got to know what's the original freezing point of water. 0. So we're going to take the OG, okay, original freezing point, and we're going to minus the delta T because that's depressing. It's subtracting that, and we're going to get the new freezing point. Okay, so that's 0 degrees Celsius minus 1.9716. I know this is simple math, leaving us with a negative 1.97. You can stop there. Degrees Celsius is our new freezing point. That's it. So you write all your givens down. You start to identify who's solvent, who's solute. Think about what you need from each of them. Write your chem equation. Check, make sure you have everything you need. The constant's going to be in kind of in your notes or in the textbook, and then calculate, and then kind of apply that to the situation given. So that's our boiling point one. Same story, but I'm sorry, that's a freezing point one. Same story. Let's do it for the boiling point. How will it change the boiling point? All right, guys, you gotta tell me what's the only thing that's going to differ here. The K value, right, in our final temperature. So I'm going to do this one in red. What's my K value for boiling point for water? Degrees C per molal, right? Okay, so how does that change all this information? What's the only thing that's going to change in my formula? K value. So delta T is going to be KIM still. So K being, in this case, 0.512 degrees Celsius per molal. I factor is still 1 because it's still that sugar. And then the M value, we already calculated by moles divided by kilograms of solvent, is still 1.06 molal. What is my change in temperature for boiling point? Say again? Degrees Celsius, right? All right, so the boiling point is not as nearly as impacted because it's constant, it's a little bit smaller. So how do I get the new boiling point now of water? What's it called? Boiling point elevation. So what does that mean? You add it, you don't subtract it, okay? So what's the original boiling point of water? 100 degrees Celsius. We're going to add the delta T here. And we're going to get our new boiling point of water, which is now what? 100.54 degrees Celsius. Or so. So just a little higher, not significant, but still a little higher. Who feels okay so far? Give me like a little hand, like All right, I'm gonna stop. I'm gonna let you approach number 2, and I'm gonna come around and help you guys as you go. So number 2, notice it's similar, but read it carefully as you go. Do this one in your notes. I'm gonna come around and help you guys talk to each other about this as you go. Yeah. That's high. To get the molality units are moles of solute per kilogram of solvent. So I used it just to find the molality. I erased it because I was running out of space. But when we took moles divided by kilograms of solvent, we got 1.06 molal, and that's what we've been using for the molality. Okay.
Bottom one, two.
Yes, so oh, yeah, yeah. Sorry, double that. Okay. All right, guys, come back up here. Attention-wise, let's make sure that you understand when you're adding, subtracting, and what each part will deliver information about. So, ready? What's really the only difference between a question 1 and question 2? The I factor. And that's because the ionic compound comes into play, the I factor becomes larger. So, what do you notice is the big difference between the delta G's here? They are higher with ionics, right? But in this case, it's just doubled, right? So the freezing point depression of sucrose was negative 1.97, whereas the freezing point was double. It was about 2, is about 4. You see that? So the I factor being 2 is doubling that. And then same thing for boiling point. It's going to go up by about 1 degree, whereas the other one went up by about half a degree. So this would be 100.6 degrees Celsius as the new boiling point. So in this case, who causes a more significant depression or elevation, ionics or covalence? Ionics, so sugar or salt? Salt for sure will have the greater effect. And then why? Okay, so the number of particles are what's going to be causing a more significant increase or decrease in our temperature changes. So whenever you have to make a comparison, and I don't give you all the information like moles and kilograms and anything else like that, I just give you the identity of the compound, you should be able to tell me who's going to impact the freezing point or boiling point the most. So let's go through this last example and then let you guys work on your lecture problems for yourselves. Compound carbon tetrachloride. What's the formula? How did you know that? You identified in your head as covalent, and then you saw the prefix. Well, the prefix really helped, right? To see it as covalent. And then go ahead now, what's the I factor? Because it's covalent, it doesn't ionize, right? Okay. Sodium chloride? NaCl?
2.
I is 2 because it ionizes into 2 ions, right? So you should be able to tell me who, in this case, between calcium chloride and sodium chloride, carbon tetrachloride and sodium chloride, who's going to cause the lowest freezing point? Why? Okay, so this is going to depress the freezing point more because it's going to cause a bigger delta T. Okay, so sodium chloride will definitely cause a lower freezing point. Who will cause the lowest boiling point? Lowest boiling point. Why? So what do we do with boiling point? Boiling point, not depression, elevation. So this guy with the I of 2 is going to cause the greatest delta T that we add to the boiling point. So it's going to cause the greatest boiling point or the highest boiling point elevation, where so this is going to have the lowest boiling point because it doesn't elevate it as much. So you can see how the questions become more qualitative and quantitative. All right, if you feel okay with this, pull out the lecture notes, which is on the bottom of 1 through 18. And I will pull up the K values, which are from the textbook. You guys have about 30 minutes or so. There's only 8 questions here. Now, they start to include solvents like methanol, benzene. They start to give you more specific names like antifreeze, which is ethylene glycol, or sodium chloride. So I did 2 really simplistic examples with you. These might be just a little bit more. That's why I want you to get 1 through 8 done. 1 through 8 done with me in class. You see what these are in your lecture notes? If you need to move to a lab station because you need some space, do that. You can work with 1 person right now. That will give you the benefit of having some talk time to give them a chance to let things sink in themselves as well. Let me know how you doing, okay? Yeah, I'm gonna call some people up here. Let me just finish this video. So you're doing these lecture problems. Remember, Van Top factor is the number of particles. And then your constants are here. If this is something you want to take a picture of, feel free to, but it is on page like 495, 496 in your textbook. I am going to call up some folks. I need to see like thermochem foldables. I need to see some 1 through 18s. I need some of your close reading. So I'm going to make sure I talk to as many of you guys today as I can. So a couple of you guys are moving ahead. I'm going to go ahead and let you see some of these answers as you go. I'm going to leave it up like this though, so you can see. Well, do I need to scroll back up for the K values? Did you write those down? Or did you take a picture? Okay, I'm going to scooch it down. I'm just going to actually do this. So as you're considering who's the solvent and who's the solute, the larger quantity is the solvent, okay? So don't fret if you hear like, I don't know. And if I ever give you a sample and it just says solute, it doesn't give you information, be it ionic or covalent. If I just say solute and it doesn't say ionic or covalent or any other information, assume it's I of blank, because I don't think you should be able to assume anything other than that. So keep checking as you go. Give me a hand raise when you need me. I'm going to upload this video so that my couple people who are still working on this can watch it.